Okay, everyone, welcome back to our Calculus 3 class notes. We're now on page 100 in section 15.5, and we're going to look at example 89. So remember, we're working on triple integrals. We've just got introduced to triple integrals over rectangular coordinates. So we're setting up the limits of integration for evaluating the triple integral of a function, f of x, y, z, over the tetrahedron D, which has vertices 0, 0, 0. So I'm drawing the picture at the same time. Vertices 0, 0, 0, 1, 1, 0, and 0, 1, 0. Those are all in the xy plane, and then the other vertex at 0, 1, 1. So when I connect the vertices, I can see this prism looking thing. Okay, now the region in the xy plane is this triangle down here. So when I transpose that over here to just look at the xy plane, and I'm shading in the region. Okay, so this is the line y equals x. And then this is the line y equals 1. And this, of course, is the y-axis. So here I have that region. Okay, now I want to find the triple integral of some function f over that tetrahedron. So this is the domain D, this actual domain D. This is the domain R down in the xy plane, which will take care of the integrals for y and x, the dy dx portion. Now let's see what I want to do for the z portion, okay? So what I need essentially is the equation of this surface, which is a plane, right? This surface right here, this triangle that's slanted here, this is the plane, z equals some plane. So I got to figure out what that plane is. Now to write down the equation of a plane, remember I need a vector normal to that plane and any point on the plane. So I certainly have this point on the plane, or 0, 0, 0 even, or 1, 1, 0 I could use. But I just want to find this normal. So now the normal here is going to be perpendicular to any two vectors I can find in the plane. So I'm going to use the vector from 0 to the point 0, 1, 1. So that's the vector 0, 1, 1. And then I'm going to use the vector from, let's see, I'm going to use the vector, I use the vector from the point 1, 1, 0 back to, actually I use the vector from 0, 1, 1 to 1, 1, 0. Should have used this vector, would have been a lot easier, but that's okay. So I use the vector from 0, 1, 1 to 1, 1, 0. Actually, vice versa. I use the vector from 1, 1, 0 to 0, 1, 1 because 0 minus 1 is minus 1, 1 minus 1 is 0, and 1 minus 0 is 1. So that's the vector. I could have chosen an easier one on here, but don't worry, that's what I chose. To get a normal vector, when I take the cross product of those two, I get the vector 1 minus 1, 1. Then if I use the origin as my initial point, so this is my normal vector. Remember my formula for the equation of plane is if this has components a, b, c, it's a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And then when I simplify this, I get z equals y minus x. So here's the equation of that surface, the plane. So when I integrate over the domain D of f of x, y, z dv, the dv becomes dz dy dx. So z goes from the surface, z equals 0, the plane down here, z equals 0 in the xy plane, up to the plane z equals y minus x. So these are my limits of integration for z. And then I look back to R here, the region in the xy plane, to find my limits of integration for y and x. So my outside integral is x, which has to be constant. So as x goes from 0 to 1, the y integral goes from the function y equals x up to the function y equals 1. So my limits of integration are 0 to 1 for x and x to 1 for y.